Hello everyone, I am Yang from Department of Material Science and Engineering. The topic of my video project is silicon germanium lithographic quantum dots for quantum computing. Here is the outline of my presentation. At the beginning, I will introduce the motivations of why we want to build the quantum computers based on silicon, what the advantages of silicon are, and a brief historical review of realizing spin qubits in silicon. Then I will talk about two typical architectures of silicon quantum dots and show you some state-of-the-art device performance. Lastly, as the outlook for this topic, I want to point out a few critical challenges and discuss future directions. Now, let's begin with the motivations. What are the advantages of silicon as a material for quantum computing? First of all, it is a fundamental material of semiconductor industry. We can make use of the established device structures and fabrication techniques when we develop the silicon-based quantum computer. Secondly, it has superior spin co coherence time relative to other semiconductors, which is due to the low hyperfine interaction to nuclear spins and the reduced number of nuclear spins. As shown in this box, compared with its major competitor gallium arsenide, which has tens of nanosecond coherence time, silicon germanium heterostructure has hundreds of nanoseconds as reported in 2012, and it can achieve even longer coherence if high purity silicon is used, which has amazing coherence time of 10 seconds. Now let's come to the historical review. The story of discovering qubits in silicon is about transforming barriers into innovations. Governed by the Moore's law, silicon-based transistor encountered quantum limits when it went down to nanoscale. Some people soon realized that we can actually take advantage of this barrier. It means we can build devices on coherent quantum effects and use the quantum state of spins to storage information. There are two ways proposed to realize spin qubits in silicon. One is the naturally confined donor bond spins, firstly proposed by Ken in 1998, which we are very familiar with by our reading. The other one is the artificially defined lithographic quantum dots, first proposed also in 1998, and the latter one, quantum dot, is my focus today. Now let's move to the section of device function. There are two typical architectures. The first architecture of a silicon quantum dot qubits is for single-shot readout of electron spins in a single quantum dot. The measurement of spin state is based on spin charge conversion. The tunneling of an individual electron is controlled by spin. It works in the way as follows. Quantum states of spins in quantum dot can be split by an applied magnetic field. Gate voltage is tuned in such a way that electron tunneling of the dot to a nearby reservoir only happens if it is in the spin-up state. The signal from the charge sensor changes only if the electron moves. Therefore, a non-zero signal corresponds to the spin-up state, and the zero output means spin-down state in quantum dot. It can be further illustrated in this figure. If a spin-up electron is loaded as shown in A or C, it will tunnel into the barrier during the readout and replaced by a spin-down electron, which gives a readout current as shown here and here. However, if a spin-down electron is loaded as shown in B, no current will be read out because of the energy level of quantum dots is lower than the reservoir and the Pauli exclusion. So the readout current indicates the spin-up state. Another typical architecture involves singlet-triplet qubits in double quantum dots, reported 1 year later. Now it has two quantum dots controlled by several gates as shown in this picture of the device structure. Electrons can be loaded into the quantum dot from two reservoirs as the straight arrows indicate, and the quantum state is dominated by the occupation of two quantum dots. For example, 1-1 state in this case means each quantum dot has one electron. Triplet spin states exist in a system with two spin 1/2 particles. There are four possible spin configurations: spin up in one quantum dot, spin up in another one, both quantum dots have spin down electrons, or one is spin up, one is spin down. And these three states form the basis for spin equal to 1, 1, 1, 1, 0, and 1 minus 1, which is called the triplet state. And there is only one basis for spin equal to 0. That's why it is called the singlet state. Now consider a gate pulse that transfers the double dots through 0, 1, 1, 0, and 0, 2, which means an electron is transferred from the reservoir to the left quantum dot to 1, 1, and then to the right one, which gives the state of 0, 2. Because of the energy of triplet 2, 0 state is higher than the triplet 1, 1 state, and the spin conservation together with Pauli exclusion, only the singlet 1, 1 state can transit into singlet 0, 2 state. This phenomenon is called Pauli spin blockade, and it is revealed by the change in conductance of the quantum point contact between 1, 1 and 0, 2. Therefore, similar to the previous case, now we have two distinct cubic states, singlet 1, 1 and triplet 1, 1, and only the singlet 1, 1 state yields a non-zero output during the 1, 1 to 0, 2 transition. That's how we can measure the spin state in the double quantum dots. Now, if one modifies the singlet triplet energy splitting J, it will produce a Rabi oscillation as shown on the left. In addition, we can also get the coherence time T2 star as we tune the energy splitting. Moving to the state-of-the-art performance, people have developed quantum dots in isotopical enriched silicon in 2014, which gives a 120 microseconds coherence time, which is several orders of magnitude enhancement. Moreover, hybrid quantum dot cubic of spin and charge was also proposed. It features with fast rotations and high fidelity manipulations. As for the outlook, there are a few challenges of lithographic silicon quantum dot qubits. The first one is its large in-plane effective electron mass. This large electron mass will shrink the electron wave functions in quantum dot. Therefore, as a result, smaller devices are needed to isolate electrons. Secondly, there exists valley degeneracy in silicon's conduction band, which may affect the spin blockade. Lastly, the manipulation uh, of spin qubits in silicon requires ultra-low operating temperature, which means any defect or trapped charges that can be ignored at room temperature may be very important at such a low temperature. Therefore, ultra purity of silicon is required. We need a very careful control of defects. For the future directions, future development of silicon quantum dot qubits can be focused on combining approaches on donor atoms and on quantum dots, because these two different approaches has individual advantages. Donor atoms usually have a long coherence time, and quantum dots has a feature of high tunability and easy control. Secondly, we can seek for manipulation or readout of multiple spatially separated qubits, which can work as a multi-level quantum information processing. Lastly, we can make use of the current technology in semiconductor industry to make arrays of silicon quantum dot nano devices uh, as it is in a real high in a real processor with high density.